Okay, thank you. So, yeah, for my last lecture, I'm going to have much less mathematics in it and much more pictures, so I don't know if that will make you happier or not. What I want to do is to go through some ideas of, we presented the different algorithms of data assimilation. I want to explain, just give you some pictures of some different areas in which this has been used, because I've used a lot of the example for weather prediction, but it has been used in many different environmental problems. So I spend some time going through that, and then I want to spend some time looking at what are the real challenges that we're facing as researchers now, because the way I presented it, it can seem as if we've solved the problem, and instead there's lots of things we still don't know and we're still trying to work on. So the first application, I'm going to stick with the numerical weather prediction. You may have seen diagrams like this, or you may not. This is from ECMWF. It's a measure of the forecast skill score. It's a 500 millibar height from going from 1981 to 2015. So if you look, for example, the blue line is a 3-day forecast. The accuracy of a 3-day forecast, the top line being the northern hemisphere and the bottom line being the southern hemisphere. And then we have for a 5-day forecast in red, for a 7-day forecast in green, and for a 10-day forecast in yellow. And things you see, apart from the fact that you see the forecasting accuracy increasing, you see, if you look along here, for example, a 5-day forecast now has the same accuracy as what a 3-day forecast had in about 2017, about 20 years ago. And this is a standard thing that we gain more or less over the last few decades, each decade, 1 day of predictive skill. But what's interesting, you see, the top line in each of these is the northern hemisphere, and the bottom line is the southern hemisphere. And there was a big difference between them, and suddenly they start coming together. And of course, that's going to be due to many factors, including our modelling. But one big thing is that to be able to use satellite data in the southern hemisphere. And if you look here at this point, was where the ECMWF introduced their more advanced 4-dimensional variational assimilation scheme, and this point was where they updated the scheme. And you can see it's not coincidence that these updates coincide with the southern hemisphere forecast being almost as good as the northern hemisphere forecast, because we're much better able, by implementing these data assimilation techniques, we're able to make much better use of the satellite data over the southern hemisphere, and therefore get better forecasts of what's actually happening in the weather over the southern hemisphere. Now, this is going to be a mix of just a whole host of different things. This is, again, weather prediction, and this is related to what happens. So I spoke about this P matrix or B matrix, which holds the covariances. And what I didn't have time to go through in detail is that this really determines how observations at one point influence the field at different points. So if we look on the left, this is at the surface. What we've had put here is we just assimilated one observation into a 3D bar scheme at this point here at 500 millibars. And what happens is, or 500 hectopascals, we don't just increment where the observation is, but we want to put a smooth increment into our background field, because if we just had a spike where the observation was, it would make things go unstable. So what happens is that we have these circular contours, which essentially say, and these are determined by this covariance matrix, which say if we have an observation here, this is how we should update the field around it. And not only around it at the same level, but also lower down in the atmosphere at 1,000 hectopascals, we've also got information about the observation, which is from 500 hectopascals. Now these, why are these perfectly round? This is because the way we design our 3D bar systems and the way we design these covariance matrices, what people are trying to, or if we look at a 4D VAR, and Javier mentioned this a bit in the practicals yesterday, if you remember, the Kalman filter evolves the covariance matrix from time step to time step. Within a 4D var, there is some implicit covariance within the time window. So if we have the observation at the start of the time window, we would get this. But if we have the observation at the end of the time window, we get a non-circular increment to the field around us, depending on the flow. And why this might be important. So if we have, for example, a front, which is a strong gradient of temperature, an observation of one side of the front really is not telling us what's happening on the other side of the front. So we want to spread the information along the front in a dynamical way rather than just a round way. And you see that by using this 4D var system, so this is an illustration of the value of 4D var, it's able to use the dynamics in a certain way to shape these increments, the increments meaning what we add on to the background to get our analysis, is shaping these increments according to the local dynamics. So one question is, can we get more flow dependence on this by combining variational methods and ensemble methods? So we saw that the ensemble methods predict this PF matrix. So they have the covariance matrix depends on the flow. We usually just in the 3D val or 4D val at the start of the window just assume this B matrix. Can we combine them in some way? And that's what people are looking at the moment. And there's various proposals with all kinds of complicated names. So we have ensemble 4D var, we have 4D ensemble var, and we have ensembles of 4D ensemble var, and various other combinations of those names. And these are all different ways that people are looking at the moment to say, can we combine some of this information about the current flow with our usual covariance matrices to try and improve our assimilation? And this is an example from the Metaoffice. If we look at the start, this is from the 4D var. What we've got here, if you look at the top first, this is the standard system. What we're doing is having a single observation of the zonal wind, the east-west component of the wind there. And the colored contours show the response or the increment, the wind increment that produces. And in the background, we see the temperature contours. So if we have something at the start of the window, we have, as before, just a round increment. We're not taking account of the flow. Here, though, if we have an observation at the end of the 4D val window, you can see here we have a temperature gradient, or a front, if you look at these contours behind. And what we're doing is, as I said, spreading the information along this front rather than across the front. Now, we can't do that at the start of the window, because at the start of the window, the 4D var has not yet run the model. It's not had time to evolve. So can we do this combination? And this is what this current Metaoffice combination is doing. And now we see that if we combine some of these standard variational methods with some of these ensemble methods, we can actually get the increment from this wind from the wind observation to have some dependence on the flow even at the start of the window. But this is something, so this seems to work in this example, but how to get this working in practice and how to really combine some ensemble information with the variational information is still a very open question, and people are comparing many different methods. I spoke yesterday about the ensemble common filter and localization. This is an example of this. So this is an example of what happens if we don't use localization. So if we only have, this was run by people in Japan, Miyoshi et al., so using an ensemble common filter. And what I said, that if we don't use these localization, if we just generate use the ensembles to generate covariances, we can end up with ensemble noise. So if you look in the top left picture, A here, this is from just 20 ensemble members in our ensemble common filter. And here we have some kind of signal, but you can see we have lots of noise, which is spurious just because we don't have enough ensemble members. And when we use this localization, we get rid of all the noise, and we just keep the signal we want. So what we've done is just set to 0 everything outside a certain radius. But is that the right thing to do? And because they have a huge supercomputer here in Japan, a 10 petaflop computer, what they tried is increasing the number of members without localization. And as you increase the number of members, say from 20 to 80 ensemble members, you see a lot of this spurious noise disappears, but you still have some. Then you increase it to 320 members, and you still have some noise. But the interesting thing is, when we increase it to 10,000 members, which is huge, you could never do this. I mean, normally if you were running this on an operational model, the most you could do would be about 40 or 50. Here, because they have a huge supercomputer, they managed to do 10,000 on one experiment. And this is what they get as the signal as the true correlations. And this is interesting because you see, when we just do our standard methods with localization, so plot B on the top here, we just keep this little bit here. But what this is telling us that probably the real correlations is not just that little bit here, but is all these parts going along here, which is also some kind of flow dependence. There's some upstream or downstream dependence on the true correlations, which we should be taking account of, but we don't when we just do the standard localization. So in practice, we're never going to be able to run this number of members. So how can we do the localization in an intelligent way so that we keep this kind of structure rather than this kind of structure? And that is something, again, which is an open question as to how really best to do this in practice. That's all on weather prediction. There's a lot of work in the oceans now from ocean data assimilation, well, there has been for many years, and ocean prediction. But over the last 20 years or so, there's been this huge array of buoys. These green dots here are floating buoys, which essentially float about under the ocean, below the ocean, and every 10 days they come up to the surface, and as they come up, they measure the temperature and salinity of the surface, and they beam that to a satellite, and so every 10 days you have some data from these. And we also have data from ship tracks and from some stationary mode buoys. And so it's not as much data as we would like and as we have in the atmosphere, but at least we can do reasonable ocean data assimilation with this. This is an example from the Metaoffice where they're starting off with some kind of model background. So this is their sea surface temperature background from some kind of a forecast. And they can have observations from those buoys of temperature and salinity. And also from satellite, they have observations of the sea level anomaly and of sea ice and sea surface temperature observations from satellites. And what we want to do is combine all this, and we can do an analysis of temperature, salinity, sea surface height, and sea ice analysis. And this is important for applications such as fishing, but also for things like the Navy, for submarines, etc. They need to know the structure, the temperature structure, under, not only at the surface, but also under the ocean. So there are many applications where we really want to do ocean data assimilation. This is another example from the Metaoffice where we have observations at the top of, these are profiles of temperature, so going down to 250 meters along a line of latitude. So this is longitude here. And this is their previous assimilation system and their new one. Now it's hard to tell from this which is the best. But what I just want to get the idea is, we're not just interested in what's happening at the surface of the sea, but we're also trying to get this structure like this of what's happening under the ocean, which is important for many applications. So this data assimilation within the ocean is also a fundamental application and is used operationally in many centres. Now, one interesting thing about when you're doing a simulation of something like sea surface temperature is what do you mean by sea surface temperature? And this is an interesting diagram because it shows that in the top part of the ocean, the temperature varies very much. So this is what happens at a typical nighttime situation. So this scale here is going from 0 to minus 0.3. At 10 micrometers, the temperature is minus 0.3. At 1 millimeter, it may be down here, and then it goes straight down here. So you've got a difference between 1 meter and 10 micrometers of about 0.3 Kelvin. If we look here at the daytime, we get something the opposite, where we actually have a difference of about 2 Kelvin, and we have this kind of structure. Now, why is this important? Because a typical ocean model is has a finite resolution, and maybe your top level in the ocean model is calculating the temperature at 1 meter. So your model is representing this green cross here. Whereas if you use a satellite to measure the sea surface temperature, what you're measuring is the skin temperature, which is here. And so you can see this is where, when we had the y minus hx, the difference between our observation and our model, you really need to think carefully with certain data, are we comparing the same things? Because what we call the sea surface temperature in our model is not the same as what the satellite sees as the sea surface temperature. And so when you're doing the data simulation, assimilating this kind of data, you really need to think about this kind of structure, and people are trying to introduce within the assimilation some kind of model of this kind of structure at the top of the ocean to help better assimilate the sea surface temperature data. Another example is ocean color, which I think was mentioned the other day by one of the speakers. So ocean color is essentially a measure of chlorophyll, or where there are many phytoplankton, which are important for the carbon cycle. And we can measure this chlorophyll from space, and the question is, can we assimilate this into these biogeochemical ocean models? And this is an example from some work in the UK. If I just look on the left, this was a reference solution. So this was a twin experiment where we know the truth, like the kind you've been doing in the practicals. A reference experiment, an assimilation, and showing the difference. And what I just want to bring out here is that what we're trying to show is that here we're looking at assimilating pseudo observations of satellite measurements of chlorophyll. And we can see that we can get a pretty good in some places, but there are also areas where the assimilation, we're not really capturing things yet. And so what we're trying to do is trying to improve these assimilation methods, and these are people working in Plymouth in the UK, using these assimilation methods, trying to improve them to see if we can better use chlorophyll measurements from satellites to try and map and predict the phytoplankton blooms, which are important for oceans, for example, for fishing, etc. This is another example that we looked at, a very different example of what we call bathymetry. So bathymetry is, for those of you who are not aware, basically the height of the ocean or the seabed. And this is an area in the north of England where it's in this bay, the sands move very quickly. And so within a few years, you can have changes of several meters in the bathymetry. And this really makes a difference as to whether this is the ocean here or the sea and the land in grey. This can really make a difference as to whether the local towns are going to get flooded or not. So what we said is, can we use measurements of some kind of measurements of the bathymetry and assimilate those into some kind of model? So what we have here is a model of the sediment transport linked with the model of the water flow. So we're really modeling the sediment transport, the sand flowing through the bay. And the kind of measurements we're using are what's called SAR, synthetic aperture radar measurements from which they can take from planes in order to measure the bathymetry of the local area. And what we see here is, so on the left is our prediction, or the areas in the predicted bathymetry compared to a truth one without assimilation, and on the right with assimilation. And you can see orange here and the purples are plus or minus 4 meters. So this is quite large errors in the bathymetry. And what we can see is by assimilating this data, we still have some areas of large errors, and in particular up here. But in areas like this, or in areas like this, we really have managed to reduce the errors in our predicted bathymetry. We're getting a much better idea of what's happening in the ocean, in the seabed, and therefore, hopefully, using this kind of technique, being better able to predict local flooding. So the idea of showing this one is what I want to give you the idea is this is a completely different kind of model than the ones I've been referring up to now, because what we're doing here is modeling the transport of sediments within the bay, and yet we can even use data assimilation with this kind of thing in order to try and make better predictions of what's happening. So you've heard quite a lot about the carbon cycle, and this is an illustration again of the carbon cycle, in particular over land. So these are the gigatons per year of the carbon balance. I think the yellow are the natural fluxes, and the red ones are the anthropogenic emissions. And you can see, and I think you've heard before, there's a lot of transfer of carbon between, say, the plants, the land, and the soil. And in terms of the global carbon budget and understanding the global carbon budget for climate prediction, one of the main sources of uncertainty is what is the carbon budget and what is the correct carbon balance and the correct fluxes over the land. So the atmosphere and the ocean are reasonably well constrained. And for the land, what we tend to do is say, okay, we know the ocean and the land, we know the atmosphere and the ocean, we know the total, so the rest must be the land. But what we want to do is to try and improve on this and get a better handle using data, well, in this case, using data assimilation of what the fluxes over land will be. And this is an example done by Ewan Piddington, so one of the people who's doing the data assimilation practicals, when he was a PhD student, he did with us. And what we're looking here is we have a model of a forest. It's called the Dalek model, so it's the one that Sean Quigan introduced yesterday, or he mentioned yesterday. I think it's a variation of the same one. And what we did here was an assimilation over 1 year of observations using 4D VAR over one window, and then we did a 14-year forecast over the period from 2000 to 2013. And what we're plotting here is over that period of the forecast, so we're not looking at the observations we've actually assimilated, we're just comparing with later observations that we've not assimilated in our forecast period, and we're comparing those observations with the model predictions. So this is, if you look on the left, this is the model prediction on the y-axis and the true observation on the x-axis. And if our observations and model were perfect, they would all lie on this line. What we get is reasonably good. It's a correlation of 0.79, but a root mean square error of 4.22. Oh, sorry, this was with assimilation. We're using the standard assimilation. When we had no assimilation, this forecast was much worse. So by doing the 4D VAR assimilation, we can get a reasonably good match, and the RMSSC is a bit high, but the correlation is good. What we then introduced was say, okay, a lot of these observations are made at the same site, and we're assimilating lots of, over the 4D VAR time window, which is 1 year, we're assimilating lots of observations at the same site. And if those observations are made by the same instrument, it's likely that the errors are going to be correlated. They will be correlated in time. So what Ewan did here was to introduce into the data assimilation an allowance for the fact that the observations are correlated in time. And that's what we see in the right-hand plot. So it's the same as the left-hand plot, but now allowing for the fact that we have time correlations. And we see we get a much better fit to the future predicted observations, now with a correlation of 0.88 and reducing the mean square error to 2.38. And these are, as I said, are not the observations that have been used in the assimilation. These are independent observations that we're trying to predict. So this is an example of where I think one of the things I want to get across in general in these things, and I think comes across nicely here, is that when you're introducing a simulation, we've been through the standard equations, etc., and you say this is a scheme. But when you actually come to implement it, you really need to think hard about your own system. What is your model? What are your observations? And how are we going to really adapt the algorithm to make sure that the assumptions we're making really match what our system and our observations are like. So in this case, for example, the fact that we had time-correlated observations, we adapted the algorithm to allow for that, and we see it gives a big improvement in the data assimilation result. So we really need to, whenever we're implementing these things, to really think about our own system and about how we're going to implement them. Another big area that's coming online now is coupled atmosphere-ocean data assimilation. Now, why is this important? Well, if you think over the ocean, the sea surface provides a lower boundary for the atmosphere. So the temperature of the ocean, the sea surface temperature, is very important for what's happening in the lower atmosphere. And when we're doing seasonal to decadal forecasts, it's really important to initialize this properly. However, the atmosphere and the ocean have very different timescales and space scales. And so what people tend to do for the moment is they do data assimilation on the atmosphere, do data assimilation on the ocean, put the two solutions together, and then run your coupled model. But the problem with that is that at the interface, you've not got a consistent analysis. Things may not be consistent. And so that when you run the forecast, you may end up with slight imbalances, at least at the start of the forecast, which are just due to the fact that you've not initialized the coupled system in a proper way. So what forecasting centers want to move to is, can we do data assimilation on the whole coupled system, even for numerical weather prediction? So for the standard weather prediction, the Metaoffice would like by 2020, so not far away, to be running a coupled data assimilation system. And the advantage of this is also not just this initialization, but if we can do some kind of coupling, an observation near the surface, say, of the atmosphere can tell us something about the ocean and vice versa. So we can really use the observations in a better way if we can get this to work. So there's a lot of research going on into this at the moment. A big question is whether we should use variational or ensemble methods. And this is, so the Metaoffice and EWF are introducing variational methods, but are kind of approximate variational methods because they don't want to develop the adjoint of their full coupled model. It's too difficult, too technically difficult for the moment. So it's what we call a weakly coupled system, which is partly coupled but partly uncoupled. There are other centers, for example, NCEP in America, which are using ensemble methods. And the advantage of ensemble methods, as we said yesterday, we don't need an adjoint. We can just put our coupled model into the ensemble common filter, for example, and get an analysis. Okay, simple. So what's the problem there? Well, you need to think then about localization. And what does it mean to have the different localization scales in the atmosphere and the ocean, and how you deal with this? So whichever way we go, there are still lots of questions. But people have got first results on this. So this is an example from the ECMWF, where what they did is put a single observation into the of temperature into the ocean. So this is plotting the ocean temperature and the atmosphere temperature at the start of the assimilation window. Now you see, because of the way this coupling works, and they have this weak coupling, at the start of the window, they have an increment in the ocean, according to this temperature observation, but nothing happening in the atmosphere. By the time we get to the end of the simulation window, which is, in this case is 12 hours, this is the change they're making in the atmosphere according to the ocean observation. So this means the way this is set up, that by using the ocean observation, we're saying the ocean observation is near the surface, it is telling us something about the atmosphere, and we're managing to build that information into the data assimilation system. However, we would like to do that in a more consistent way, and this is something we've been looking at in Reading, for example. So these are experiments we did on a very simple one-dimensional column model. So it's a one-dimensional model that we can run lots of experiments and get lots of data on. And what we're plotting here is, if you just concentrate on the left for the moment, it was a certain point in the South Pacific, we're plotting the correlation between the ocean current speed and the atmospheric wind speed. So here is going along the x-axis is the surface of the ocean going down to 200 meters. And here, going on the y-axis, is the surface of the atmosphere going up to 10 hectopascals. And so what this is saying is, in this case, in the boundary layer of the ocean, the boundary layer of the atmosphere and the mixed layer of the ocean, we have this big positive correlation. In other words, that our wind speed in the atmosphere, so if we had a wind speed at 900 meters, for example, here, it would be very correlated with the speed of the ocean current at 10 meters. And so that means that if we had an observation of the wind speed, it should be telling us something about the current and vice versa. So if we can build these correlations into the system, we can really make use of this. However, what we did, we split this between day and night, and we looked at this was at the daytime. When we look at the nighttime, we have a little bit of positive correlation and then a lot of negative correlation here. We see it is completely changed. And this was in December, and we also found that it changed according to season. So ideally, we would like to build this information into our systems. But if these correlations change between day and night, and they change from season to season, so they're going to change between places on the globe, the question is, how can we reasonably first diagnose what these correlations really are for a full model, and then build into our systems? And this, again, is something that people are still trying to work on and trying to understand. I want to talk a bit about reanalysis as an application of data assimilation. And this may be something that, if you don't do data assimilation, it's quite possible that some of you will use reanalysis products from ECMWF, the Area 40 or the Area Interim. And what is reanalysis? That they tend to, so the Area 40, what the ECMWF did is they went back over 40 years and said, let's run for 40 years our current data assimilation system using cycling, doing a forecast, assimilating every 12 hours for 40 years. But we assimilate using the same system a whole 40 years of data. And that means that we have a consistent record and consistent set of analyses over those 40 years that people can then look at and use for different things. And the Area Interim was a later one, which they did for a period of, I thought it was only 15 years, maybe it's a bit longer. And these products are available from ECMWF, so that you have a series of analyses over 40 years that you can pick out and compare what's happening, with the knowledge that they've been derived all using the same model and same data assimilation system. However, you need to be very careful when you do this. Can we calculate climate trends from these reanalysis data? And this is a very nice illustration published in 2004. So this is showing the anomaly in the integrated water vapor between 1958 and 1998. And what you see here, around 72 or 73, there is this, seems to be an abrupt change in what's happening with the water vapor. And if we plot a trend through this, we get this black dotted line going up here, which is a positive trend, quite a large positive trend over these 30, 40 years. So the question is, this is just looking from the reanalysis from the era 40. Is the water vapor really changing like that? And the question, what happened here is, if you look at, well, did anything else happen in around the early 70s? And what actually happened in the early 70s, that we got a lot more satellite data. And so from here, the assimilation is using a lot of satellite data where it wasn't before here. And so that is, but the fact that we're using more data and that we've got a lot more satellite data from this moment here is what's making this apparent trend. If we correct for that, then we get this blue line here, which is still a positive trend, but nowhere near as like the one we had before. So this is just to be aware of when we're using these reanalysis products, having some understanding of the data assimilation and where these come from can be useful, because you can see here that just by the fact that we're changing the data type at a certain time may lead to misleading information if you don't think carefully about what you're doing. Another application of data assimilation is what we call OSSEs, Observation System Simulation Experiments. So if we think in the real world, we have the atmosphere, we have observations, so we can feed them into the data assimilation, produce analysis, and we use that to produce a model of forecast, which we can then verify against our analyses or against our observations. Now, what if we decide we want to send up a new satellite instrument, but we don't know what kind of effect it will have? Can we somehow try to simulate the effect we would expect that satellite instrument to have on our data assimilation experiment? And that is the idea of OSSEs. So what we do with an OSSE is similar to what you've been doing with the experiments yesterday, but on a bigger scale, where you run one, where you have a truth run and you take observations from it. But in this case, we have a nature run or a simulated truth from our full global circulation model. We generate synthetic observations from that, and using synthetic observations which are consistent with the current observing system, plus which are extra observations which are consistent with the instrument we would like to test that we're thinking about planning, then we can do the analysis and model forecast, and we can verify against the nature run. I think usually for the analysis and model forecast, we would use a different model than the one we use to produce the nature run. And so by doing this, you can do an assimilation where we have all the observations that we would have now, and then you can do another expert analysis or simulation saying all the observations we have now plus this new instrument we would like to design and what we think that would observe, and try to test what the effect of that would be in the data assimilation. So would it actually give us any valuable information? So this is useful for estimating the potential of new instruments, and it is done a lot when people want to design new instruments, particularly in weather forecasting. However, you need to carry it out with great care. For example, the nature run needs to be very carefully calibrated to make sure that you're getting consistent results. And you need to interpret the results with care, particularly if you're thinking about potential new satellite instruments. Because if you're thinking about an instrument now, that instrument may not fly for another 10 years. And the observing system we have and the assimilation system and the models we have will be very different in 10 years' time. So this is not really giving you an exact picture of what you would necessarily expect, but it is giving you some kind of information as to what may be possible with these new instruments. So that is some of the current applications and different applications that people are using. Now I want to speak about some of the current challenges. The first one is the amount of data. Satellites produce a lot of data. So modern satellite instruments can have thousands of channels on each instrument. And in fact, this is a big problem for how we use this data and how we manipulate them. So in the current weather forecasting centers, they use less than 5% of the satellite data they receive, which is, if you think, it's tiny. So 95% of it we're just not using, we're essentially throwing away. And now we're getting more satellites with even more high spectral imaging, so you have even more channels. So there's lots of channels here, challenges in, say, big data and data manipulation, and how to get the most useful information from all these observations we have. Now, one of the problems, and part of the reason it's thrown away, is that the errors in these different channels are all correlated. And this is something we mentioned at the end yesterday. And we don't really know how properly to deal with correlations in the errors. There's two things we need to do here. One is that we need to understand what are the correlations. We need to come out with some kind of measurements. What is the correlation between an error in this channel and an error in this channel? And then we somehow need to find a way of building those correlations into our assimilation system, which, if you remember, this matrix R that we spoke about, which kept appearing in the equations, is what's representing the observation error correlations, which we often assume is diagonal. But if we want to include inter-channel correlations, we need to make this non-diagonal. It needs to be easily invertible, and we need to be able to specify these correlations. So there's a lot of current work in this area. I'll just show a little bit which has been done in Reading. So this was some observational correlations for the severe instruments, which they estimated between the different channels. And what you see here, channels 5 and 6 are heavily correlated, and channels 7, 9, and 10 are heavily correlated, but there's little correlation between them. Now, this is because channels 5 and 6 here are the water vapor channels, and these three channels are the surface channels. So you can see that with the surface channels and the water vapor channels, we have inter-channel correlations, but then not much between the two types of channels. And ideally, I mean, why is this important? Well, essentially, if they're correlated, that means they're not independent pieces of information. So we cannot just use these. If we just assume that we're not correlated, then we're assuming that we've got these different channels are giving us independent pieces of information, and that will give too much weight to the data within the data assimilation system. What people often do is to say, okay, to avoid that, we'll just increase the variance. We still assume that the R matrix is diagonal, there are no correlations, but increase the variance so that we give less weight to the observations. We know, at least for the satellite instruments, people are trying to look at the error correlations. However, what they did in this paper is, this is over one particular point. They said, okay, let's have a look at how this kind of map varies spatially. And this is, you probably can't see any details here. This is over the UK, but each one of these boxes is a box like the one I had on the previous picture, a correlation plot. You can't see the details, but what I hope you can see is that they differ. So some of them have the red box. The ones near the coast have, so if we look at this block here, which was the surface channels, near the coast they're heavily correlated. As we move away from the coast, the correlations are smaller. So we not only need to measure these correlations between the channels, but ideally these correlations should vary in space. Now, for the moment, we don't know how to, that would be too much information to calculate and to build into our systems. But we want to at least find, what has been shown is that at least including some kind of approximation of the correlations is better than including none. But how to do this in the most efficient way is still an area of research. Another thing that's very important in assimilation is bias correction. So if you remember, when I introduced in the first lecture the example of the temperature in this room and the simple scalar example, I said we assume everything's unbiased. And that's what we assume in all our data assimilation algorithms. But we know that it's not. Things are not biased. And this is an example of how in time, with certain satellite instruments, this is the calculated or estimated bias correction and how it varies in time. And it's non-zero and it's variable. And so when people are running operational weather forecasting, ocean forecasting systems, one thing that's fundamental is to monitor these kind of data, to monitor the different channels, and to correct the data for the bias before they put it into the simulation system. And so this is something, again, people are looking at. There are now ways also of trying to automatically include some kind of bias correction within the assimilation system, although it's not clear that you can distinguish for all the different observations at the same time. I didn't promise this presentation would be completely free of equations, so I'm going to introduce another challenge, which is model error. So if you remember, I said yesterday, when we're doing 4D VAR, at the end of the time window, we're comparing the model trajectory and the observations, and we're assuming that the difference between them is just due to observation error. But if we've been running the model over the assimilation window, it could also be due to model error. So can we account for that in the 4D VAR in the same way we did in the Kalman filter? And one thing we can do is, so we assume that our model, our state at time I plus 1, is equal to our model at time applied to the state at time I, but we assume there's some error, where we don't know what the error is, but as with the Kalman filter, we assume it's Gaussian, or this is normally or Gaussian distributed, with a mean of 0 and a known covariance. And then what we can do is try to estimate. So now all our x's over the time window are independent, or they depend on this eta. So what we can try and do is add on a term to our cost function. So we have our usual background. If you look at the bottom one first, the background or the observation, we have our usual 4D of our cost function with the background and the observation term, but now we're going to estimate all these etas as well over the time window. Or mathematically equivalent is to say eta is xi plus 1 minus m of xi, and so we can just estimate all these x's over the time window. And people are trying to introduce this. ECMWF have introduced a very simplified version of this in their system. And people are looking into how best we can do this, because if we can do this, it will allow us to make the window longer within the 4D VAR, and hopefully then to assimilate more observations at the same time. Because one of the problems is as we make the window longer, the model error becomes more important. One of the problems of this is known as the weak constraint formulation. We greatly increase the size of the control vector. What do I mean by that? We're not just calculating one x, but we're calculating lots of x's, or the x's and lots of etas. So we're making our original number of variables that we're trying to calculate for is multiplied by n. Although the two formulations appear to be equivalent mathematically when we write them down, we've shown that they may behave quite differently. And in terms of particularly the minimization and the efficiency of the minimization, there is a lot of work going on at the moment as to how we can make, which is the best formulation, and how we can make this minimization more efficient. And we also need, if we're going to do this, to specify what the model error covariances are. And it's not obvious how this should be done. People have made some guesses at ways of doing this, started some work, but there is still a lot to be done there. Question is, can we really distinguish model bias and observation bias? And this is a very interesting case. So this is when, within the 4D VAR system, they were estimating the model bias at ECMWF. And the picture on the left shows their estimates so that these contours are the estimates of the model bias for this particular run. And this particular square is interesting because for some reason there is a model bias right over Denver Airport. And it seems, is it just a coincidence that there is a bias over the airport? So what happens if you remove any of the aircraft data which are over the airport, and you get this as your estimate of the model bias with nothing in this square here? In other words, this is not really a model bias, it's an observation bias. There is a problem with the data. But if you think all we have in the assimilation is the difference between our observation and our model, our y minus h of x. So if we have a bias in there, we don't really know whether it comes from the observation or whether it's coming from the model. And how can we distinguish these is really a question, again, that people are working on. Another challenge is how to develop new algorithms. And this is particularly important for new computer architectures in the future, because the data assimilation schemes that we use will have to take account of these new computer architectures. And a lot of these new computer architectures are now with small, not very powerful processors, but with lots of them, thousands of them. And for example, algorithms like 4D VAR, where you're doing an optimization, a global optimization, because you're doing things globally, it requires lots of communication, and it's not obvious that it will be efficient for these new algorithms. It may be that ensemble-based methods, such as the ensemble common filter, may be more suited to those because you can split up your ensemble members between different processes, but that introduces also its own problems, such as localization and how you do the localization. There is also a desire to move towards what we call non-Gaussian methods. So all the methods we've looked at assume Gaussianity. There are other methods, particularly people are looking at methods called particle filters, which are non-Gaussian and allow you to understand more about the true probability distribution function of the posterior of your estimate. Now, these methods work so far on small or medium-sized systems, and there's a lot of work at the moment to say, can we get these methods to be efficient on large systems? Or are there new methods out there that we don't know about yet, which are going to be better for new computer architectures and are going to be better in including this nonlinearity and the non-Gaussianity? And that's something, it's an open area of what kind of algorithms will we be using in 20 years' time. It certainly won't be the ones that we're using today, but I'm not sure what they will be. There is also a move towards more coupled Earth system models. So I spoke about coupled atmosphere-ocean models. What people want to move towards in forecasting is a whole Earth system. So we've got an atmosphere model, an ocean model, a land model, a wave model, a sea ice model, all coupled together. And we're going to make forecasts. Can we do some kind of, and would we want to do some kind of coupled data assimilation for the whole coupled system, or is it better to do the different parts separately? And what's the best way to do this? And I think that will be a question which is still, there's been very little work done on that, and it will be I think there will be a lot in the next decade or two looking at this. But overall, the best algorithm to use will depend on your application. And you really, when you're thinking about some of these things, you really need to think about what is my application, what is my model, what is my data, and in the circumstances, what can I best expect, and what algorithm can I use with the system I have. So just some general concluding remarks. Data assimilation, we've seen, is potentially useful whenever you have a data and a model. So what we're always trying to do is that we've got some kind of dynamical model and we've got some data, and we're trying to use the data to keep the dynamical model on track or to estimate the current state by combining the two. And it's now been applied to many different areas of Earth science. So it was really developed a lot in numerical weather prediction and then ocean prediction. But in recent years, say the last 10 years or so, we have in other applications, in other applications, we have better models and we now have better data and lots more data. And so now there really is the potential, and people are starting to really expand data assimilation into lots of other areas. There's the launch of new satellites, for example, the Sentinel satellites, will provide many more data available for assimilation of different applications. So even, for example, chemical species. I've not spoken here about chemical data assimilation. So lots of things that we can measure from space, but this brings its own challenges, some of which I've spoken about. And so there's many research questions remain as to how to best implement data assimilation for different applications. So even when you decide on an algorithm and you decide on your application, the way you implement that, the way you need to treat the data, the way you need to derive the correlations, etc., will really depend on your application. And so I think whenever these methods, the assimilation methods, are applied to new areas, there are really lots of new research questions that come out as to how they should be done in practice. And I'll stop there. Thanks.
Many thanks for that. Are there any questions? Last questions from Professor Lawless?
Thank you for the presentation, first of all. And I was just thinking in limited area applications where maybe satellite resolution doesn't allow for detailed information and scarce surface monitoring network. So with the combination, using a combination of, let's say, chemicals or precipitation from ground monitoring stations and maybe precipitation retrievals from satellites, or chemical species pollutants from monitoring stations, or surface concentrations from column information from satellites.
Yes, I mean. Okay,
so I get that it's important to select an observational data set for assimilation and an observational data set for evaluation. Yeah. So if we have both sources, would we use one source for assimilation and the other for evaluation, or make subset of a combination of both for the assimilation and the evaluation, given that they have different uncertainties? And
I'd say, in practice, when you're doing this for real forecasting, you would assimilate all the observations you have. You don't necessarily keep any for evaluation unless you're particularly testing a system, because you want to get the best estimate you have. So, for example, in weather forecasting, we do assimilate data from the surface and data from the satellites simultaneously. Now, one interesting question, other interesting challenge that comes in there is the scales of representation that they're representing. So a satellite is measuring, say, a few kilometers footprints, and you have a point measurement on the ground. And how do you combine those two, and how do you allow for the errors in those two in the different scales? And again, that is something that people are looking at. But ideally, we want to try in practice to combine all those pieces of information. And then people either verify against the observations they've assimilated against, or they could do a forecast and verify against those for future observations, or people verify against their analyses. But in practice, you wouldn't keep observations back if you had good observations to use.
Okay, thank you.
I think there was a question at the front. I saw someone's hand go up. Too late now.
Yeah, it was more of a clarification about the correlation corrections that were made, which you presented. Were those correlation corrections made, this was the carbon cycle?
Yes.
Were those correlation corrections made for the kind of observations which you evaluated against in that respect?
No, even because what we were evaluating against in that was we did a year of assimilation in which we did the assimilation and allowed for correlations, and then we did a 14-year forecast. So doing the forecast, and we evaluated, we compared the forecast with the future observations in the forecast period. So those observations had not been assimilated.
But, so would they be completely independent?
They were completely independent of the assimilation, yes.
Okay. Even though they might be from stations which were making the same kind of observations, so they might be from the same stations that you made the observations which you assimilated in.
Okay, yes, okay. I mean, they're independent in the sense that what's important is the independence of the errors. And their errors would be independent of what's going on. Their errors would be independent of the errors in our analysis, because we have not used those, because we're assuming the observations have independent errors.
Yeah, I just have a question regarding like the spurious trend that you showed for error 40 in the past, and I was just wondering for the reanalysis of the newer generations, are there any approaches, algorithms that they are now using to kind of take care of such effects?
No, to be honest, I don't know enough about that. I don't know what people have done. So I think, yes, I'm sure there must be people looking at this, but I don't know enough in detail about, I'm afraid.